Hey, how's it going? So this is going to be a long video. It's pretty dry and boring, but just a little bit of where I'm at and updating some of this vibe coding. So basically, how to make these a full-blown Guideline 36 vibe coding off of normal framework hooks, and I'll also be updating this to the actual Guideline 36 algorithm, like once I test it. Check back for the repo just to see this updated to actual Guideline 36 version. So maybe in the future we'll do a little bit more with a chiller rotation, but yeah, this is a long video. Sorry, it's pretty dry and boring. Also want to note that if you see like my camera get a little fuzzy, I think it's might be on its way out and dying, so like it kind of fades in and it'll start getting kind of starting to focus and going in out of focus. So apologize for the kind of the quick dirty video here. That's I'm just throwing it together just to show you where I'm at, and hope you enjoy. At the time of writing this, it is August 12th. ChatGPT 5 just came out. Seems like a lot of people online are maybe not very happy. I've tried it a little bit and I'm kind of switching back to Gemini. I actually, it's okay. Still testing it out, but yeah, just some updates where I'm at. I'm still working on the PyBog project. It's basically a Python toolkit to develop bog files directly. So this is still a work in progress, kind of a can of worms, but hopefully someday we can use it to actually create a backup file for a JACE with AI. It's working for some like really simple examples where, for example, this is like a Python script, and it's I can manually create some object in kit control. So like here's the kit control average block, a minimum block, maximum block, and then with a Python API that I'm making, like we can actually link everything together. So it works on some like really simple examples. It kind of looks like this in Workbench. And I'm slowly seeing if large language models can understand it. In about 20,000 tokens. So I feed this cheat sheet into ChatGPT or Gemini, and it kind of gives them some examples of how AI is written in wiresheet logic using Python, and they seem to get it, but it's not perfect. I'd say it's only about maybe 50% done, but it's coming. I'm working on it, and so like let's pay attention to a later YouTube video in the future, and I can give some updates on that as well. So one thing I have created with that Python toolkit is some Guideline 36 VAV pressure requests. So like something I'm working on right now is kind of cutting over some of the trim respond logic that I created, just vibe coding something inspired by Guideline 36 into something actual Guideline 36. And what I do have working is the pressure request algorithm that would be attached to every VAV box in the system. I have been doing this in wiresheet logic, created with a Python script assisted by AI. So like this is one example of that where Python basically created this, but it's actually these are like the calculations for Guideline 36, where these are calculations to develop requests. So like basically this is a VAV pressure request algorithm that long story short, it will develop trim respond requests for the air handling unit based on the this is duct static pressure, supply fan, static pressure control, trim respond. So basically if the we're gonna feed into this algorithm via VBox stamper command. Also a set point defined by guideline 36 that if the VAV box stamper is greater than 95%, we'll generate one request. And then you can factor in, guideline 36 has some specifications where we compare the flow of the VAV box, that if we're 50% under flow, that will generate three requests actually. And then if we're only 70% under flow, that would be two requests. So this pressure request algorithm just for the VAV, this is working, created with the PyBog project. And something that I still have yet to do, which might take me a little while, is actually to do this in wiresheet logic for the air handling unit. This would take some time. So I'm actually doing this in a program object. So this is like the working state, just in my, this is actually just this is not on a JACE, this is just an office environment in my Windows desktop. I'm actually just simulating this. So this is the working air handling unit, duct static pressure reset defined by guideline 36. And I've just been simulating these examples. So here's a fan command. This would be our requests generated from VAV boxes. So in the real world, there could be 10 or 20 of these algorithms, and we'd be feeding all of those requests into here. This is the startup static pressure defined by guideline 36, SPO, static pressure minimum, static pressure max, startup delay, which I have for testing purposes set to 1/10 of a minute, but I think in the real world we would set that back up to 10. Then an update, the algorithm would update every 2 minutes, so I have that set to value of 2. Then by default I would be ignoring one box. Then this is a trim response, and then this is respond amount, that inches in water column for static pressure. Then this is also down here, this is the static pressure defined by guideline 36. This is a parameter that per unit of time we only want to be able to reset the air handling unit 8/100ths of an inch of static pressure. This would just cancel out any fast responses. So this is working in a sandbox environment, and I'll show you how I got here. All right, just for how did we get here with a program object for guideline 36. So I just wanted to say the normal framework, they also have some guideline 36 demos. So basically, if you would buy a copy of the normal framework, which I also use too, which I really like the normal framework, that you can actually see that they have some hooks written for guideline 36 here. So if you would actually see these on GitHub, they did a really good job at writing these. Just want to congratulate normal framework people that these are all of the trim respond variables that were hopefully all used to, that I demonstrated on the last video of like what those all meant. And so this is all written in JavaScript, and and they did a really nice job. If you would actually follow the spec to guideline 36, which I've studied this one pretty well, they they're following all of like the delay timers and everything in here. So like guideline 36 calls to do let's see, where are we? So like if we actually look and see if like there's some time values in here that like per the standard, like we're only supposed to reset trim or respond a certain amount of values over time within these time limits. So like the normal framework guys, they did like a really nice job. So per the way that this is written, and this is something I've blogged about too. It's like we could contribute to the normal framework in Java. Like for example, if we wanted to contribute a working optimal start block, which has been working really well, that we could actually take our Java code, then ask the large language model, please convert this to a normal framework hook. And I think the large language model is really good at that. And something that I am also working on right now is, this is like an older project of mine to study fault detection rules written by Guideline 36, is that these are all written in Python, mostly in analyst libraries called using pandas. So like something that I am working on in the near future, which maybe I'll post another video, is actually converting these fault condition rules to JavaScript for a normal framework. So so an example of that is, so this is the OpenFDD project, air handling unit faults, fault condition 1 defined by Guideline 36 is actually duct static pressure. If basically if the fan is running 100% and we're not meeting duct static pressure, which is defined by this, that we flag a fault. And the way that that is written in Python is right here. And then this is like the analyst coding library called pandas that basically we're doing like a fan check that if the VFD speed is greater than or equal than VFD max minus some error threshold. You know, if that fan's running really hard and not making static, you know, that's a problem. That's a fault. So something that I'm working on is in the future, which I'll do a video on, is using AI, the large language model, to convert this to normal framework hooks. So I think I actually have that here. So this will probably be another future video, but this is the output of converting that Python code to normal framework hook, which is be a really neat feature to see on the normal framework. Is we can use the Fox protocol driver that's written by the normal framework, discover a JSON through Fox, get some data flowing, and then we can write hooks in JavaScript. So this is what I'm hoping to see. Our fault rules defined by Guideline 36, converted from Python to JavaScript for the normal framework. So pay attention to that coming in the future. But something that I wanted to demonstrate today was going from JavaScript to Java. So Java is used in Workbench, in Tridium's framework, and then normal framework is JavaScript. So like two different coding languages. JavaScript, if you see this normal framework, a .js file, that's a .javascript file, which is mostly it's coding for the browser. Java for Workbench for Tridium is completely different. It's higher level language program. It's not for the browser. So at some point in time when I can demo fault condition rules in JavaScript, it's all really neat because it's almost like kind of looks like Node-RED, like you can do everything through the browser. So when you're doing stuff remotely for IoT purposes, it's really neat having functionality of dialing into a site with a browser. So yeah, let's check that out a little bit later. So I just wanted to kind of hit that point home, is that like something that I hope we can do in the future is like maybe billing automation adopts more of like higher level language coding languages, is that we can use the large language models to transfer algorithms from one system to another. And I think it's really also cool that Normal Framework is an open source platform. So they're kind of like paving the way on, and there's other companies doing this too, about like having open source examples and open source rules and everything like that. So it's, open source logic. So like hopefully I can take some of their Guideline 36 hooks written for duct static pressure and temperature reset, bake it into Tritium, and then maybe I can even contribute back to Normal Framework my Java code to JavaScript, so people can use optimal start in Normal Framework, or even fault rules. So I think that's really cool. Normal Framework is really cool too. More to come on that. So it's like, I hope that's kind of driving the point home. It's like, hopefully that's like the future, is like things are more open source, and it's like very thankful that Normal Framework doesn't have this locked behind a proprietary curtain, you know, that people can exchange ideas and help each other out. You know, this is, we're all using this to like make HVAC energy efficient, more energy efficient, save the energy. You know, I think that's, the more we can do that, the better. So, you know, thank you, Normal Framework, for being able to provide that, and we'll do some more videos on that in the future. All right, so here we are again. So back on the Vibe Code Addict repository, this was just an algorithm that I wrote, kind of inspired by Guideline 36, where you just link up all of the VAV boxes to it, and it ignores the top highest values, and it tries to keep it tries to basically float the duct static pressure down to make the open up all the boxes as high as they can go. So it's basically meant to save electrical energy by keeping the maximum VAV box, to keep the max value at 90%. So we could ignore a box or two if you want, and then it tries to keep that second highest damper open to 90%. You know, it worked pretty good. I been watching this on some other buildings, and it's been, you know, not too bad. But if we wanted to make this more Guideline 36, you know, we need to actually modify this a little bit. So this code is actually built into the README of this file. So like, okay. So for me to get to here, I actually started with Gemini. Just basically, it took me a while. Let's see if I can go all the way up in my prompt. So pushing it a lot. So basically, I fed the README of the Vibe Code Addict right into, you know, is this stuff making sense to you? I have a question, and then it says yes, makes sense. So then this is where I took the Normal Framework hook, and I copied it right into the large language model, and told it to let's revise this existing duct static pressure program into something actually Guideline 36. So this is how I've been kind of tackling this, as well as that ASHRAE does not want their official documents fed into AI providers. So I've been kind of getting around this by studying the spec offline, and then looking at the code, even testing it a little bit on the Normal Framework. You know, these guys did a really good job, so I'm just feeding their interpretation of Guideline 36 into the large language model, which is written in JavaScript, which I explained before, and converted to Java. So basically, I pushed it quite a bit. So it came up with the code initially, and I've been kind of studying the logic as it comes out, and it's actually a little even more simpler than an algorithm that I wrote. that this looks good. So it's trimming basically if it's clamping the values, it's responding, and most importantly, like I had a bug here in the slot that it took me a while to figure out. It was something on my end. So then also, most importantly, I'm simulating it in the in Workbench offline before I would take it to set it up on a JSON in the field. That like I compile the program offline to the production field environment, and then kind of run it through its paces, just to make sure that it's doing what it's supposed to do. So maybe we'll stop here on this video, and then I'll do another one here to so this is the duct static pressure reset algorithm, and then let's make a temperature reset algorithm, vibe coded in the same format. Okay, here we are again. So basically, like this README document, like I'm like feeding this whole thing into the large language model, and it's like looking at all these examples of like how we've been writing things for Workbench, because Workbench is proprietary. The AI services haven't trained the models on how to use the Niagara API. So like one thing that I've been kind of doing a little bit lately is I want to actually test this, because I think like a concept in working with these language models, like they can only handle so much input data. It's called context window. So like, and they actually it's called tokens. So like each word is considered a token. Basically it's a unit of text, kind of like gallons of gasoline, cubic feet per minute of air, gallons per minute of piping for HVAC. Like the natural language processes in AI, and that they all use tokens. So like this document could be an enormous amount of tokens. So I've been trying to see how many tokens it is, be conscious of like my token usage, which I haven't in the past. So this is 23,000 tokens, almost 100,000 characters. So like something that I think we have to be conscious of is like the language models can handle I think ChatGPT's newest one handles 180,000 tokens of context before it starts losing its brains. It'll start purging stuff first in, first out. So if you go past that context window, like I notice it when I prompt sometimes and I'm pushing to write better code, it's like all of a sudden a large language model, it's like a blank slate. I don't know if you ever run into this, but it's kind of like a felt sensation where it's like, now I'm dealing with something that it doesn't know what I'm asking for anymore. And I think I burned through its context window. So, and it doesn't tell you that. So like to keep in mind, like some language models may only have 20,000 input, or 20,000 context window for tokens. So that also includes the input and output. So like if I have 23,976 of input tokens, the context window also has to include the output. So if I'm looking for it to generate a Python program that's 1,000 tokens long, like the context window has to cover the input and the output that it's generating. So be mindful of that. So I'm kind of curious to ask, see if it even knows how many tokens it used. because I know, like, since I've been pushing it, I've probably burned way more than its context window. So let's ask Gemini, what is your context window and how many tokens have we used so far in this conversation? This is actually just a new thing I've been kind of trying to be conscious of when working with the AI services, because yeah, I'm probably burning through lots of tokens. Let's see what it says. So it's goes a little further. So he doesn't have a fixed token window, which I find that hard to believe. So they don't even know how many tokens they've used, but which is kind of interesting. So like he can't provide a specific number, but just be wary of it, because I've run into this all the time, is that when the language model starts thinking that I've lost my brain, you know, like it starts generating like code that doesn't work anymore. You know, it's like it starts doing stuff like, I know I've burned through my token limits, and it's basically starting over from scratch. So yeah. So okay, so where were we? So we wanted to generate a guideline 36 temperature, pressure, and reset. So like our duct static pressure temperature reset is working, and let's push the language model now to make a temperature, static pressure, and reset. So I do have on the vibe code one also a temperature reset, trim and respond algorithm, but like I think that this is so similar, like the variable input names and everything are so similar between duct static pressure reset and temperature reset defined by guideline 36, that I think I'm just going to reuse this. So let's see, so let's burn some more tokens. I'm just going to use my handy dandy snipping tool. So let's see, so let's take a screenshot of that, dump that into Gemini. Also, I want to do I want to just give it my slots that we've created. So this is my slots. Whoops. Okay, so these are my slot screenshots. And then I am actually just going to go back into the program editor. Let's copy that. Dump you into the chat too, and say, let's like say this is working pretty well. Now let's create a temperature reset algorithm defined by G36 for a new program object to use in the Workbench. Now spelling's a little incorrect, but okay, so I'm actually gonna also this is the normal framework hook, so let's upload that to you. So that's downloaded from the GitHub site, and like I was saying, in the future is like we're taking from normal framework and baking it into Workbench, and then someday we're going to contribute back to the normal framework from converted Python code, and maybe even some optimal start written in Java. So it's a give and take relationship. No one is stealing anything, you know, we're actually going to borrow it and contribute back. So that's the long plan. That's the plan in the future. So let's tell Gemini here, you know, let's make a temperature reset algorithm based off of the NF hook for this that was written presto. So while Gemini is thinking, I am going to jump back over here, and like I'm actually just going to just duplicate this in Workbench and call it AHU Guideline 36. Let's see, this will be temp reset trim respond. So this is our temp reset. Let's rename you here too. So duck static temp reset. And then this is our output variable. So I'm going to rename you to this will be our air handling unit. Leaving temp set point output. So this is the final variable. So, but these should all be the same. So whether it's the temperature or pressure, that they should all be the same. So one thing that I do think it's worth, let me just go back here and just go to GitHub, normal framework demo. One thing I still think worth showing, I'll just do it in the JavaScript version, even though we'll be converting this to Java, is that there's one actual thing that's a little bit more sophisticated than a duct static pressure. On the temperature reset for the air handling unit, Guideline 36 calls for these air handling unit minimum cooling supplier temperature, and then a maximum cooling supplier temperature, and then cooling min and a cooling max. So this is actually just a linear reset right here, and what it's meant to do is so basically these are degrees Fahrenheit right here. So like the idea is to limit how warm the air handling unit supplier temperature can go. So if it's, at least in the United States, I know this is degrees F, if we're above 70, more than likely it's pretty humid outside. The mechanical engineers like to use something that's we're going to be dehumidifying with air handling unit supplier tempo 55. So like what this reset is meant to do is we'll always provide some dehumidification, sensible and latent load. So this is actually like one extra step in the supplier temperature reset by Guideline 36, is they have this little bit of logic to account for humidity. In environments where I live in the summer, it gets very hot and very humid. So like there could be times in the building where there is not a call for cooling, but we're actually bringing in lots of humidity for ventilation purposes. So like this could be like early in the morning that the building is actually satisfied. There's not a big demand for cooling, but they could be really humid outside, so we still need to dehumidify the air. That this is a little bit of logic is meant to account for that. Because if we're not driving the cooling supplier set point down enough to really wring out that humidity, that will be pumping humidity into the building, which would be if once the humidity gets above 70% or 60%, the relative humidity, that like we could be running into some people feeling stuffy, or there could be even mold growth. So okay, so we're going to make sure that Gemini verified that it got this little algorithm and converted it to the Java version. Okay, so here we are. So like Gemini has completed its task. I haven't even looked at this yet. So like let's see, what are we looking at here? So this is the onStart method. So when this program starts, it looks like it's giving us some initial variables. looks okay. So this should be our default supplier temperature set point. So this is same thing I borrowed from the last program, and a normal framework hooks is like, this is the time delay in seconds, which I'm gonna ask it to change that slot name because I think it's kind of confusing. But this is a startup delay, 10 minutes. This is the algorithm interval, the ignore request. So this is like basically the algorithm that. So yeah, so it's doing this new set point, this linear interpolate, which we were talking about before. It's that linear reset to make sure that we're not pumping in humidity to the building. So it looked like it got that. And the trim respond logic looks pretty similar to the last value too. So, all right, let's use the interpolate function. So this looks pretty good. So it's doing a little linear conversion here, and AI wrote all this. It probably got converted the JavaScript version that normal framework used. So let's try and make this happen in Workbench. Okay, so let's copy this into Workbench. These are our slots, so let's just check. So we just have to feed it a couple new slots here, which I think I kind of labeled them different. Total request, fan run command. So I'm looking at this right here, that when I copy the duct static trim and respond to the temp, that our slots are named the same. So total request fan, outsider temp, which I have to grab. And then there's also discharge your set point. So this is our output variable, sp min, sp0. So I'm kind of curious, did it even have a sp? So I'm curious to do the normal framework have a sp0. Yeah, they did have a sp0. sp0 equals the maximum cooling supplier temperature. So let's see if the code base have a like the nf hook. Let's see, I also wanted to have it change something too. I think that this yeah, it did change that. So update minutes. So it does have ignore. These are Tmax calculated status numeric. So it looked like it did actually say, I just want to make sure that this is the same. Update minutes. So I'm just gonna say like, please mimic the existing slot names well, but keep the outside arrow ones like you added, and update, please. Okay, let's see what it does. I think it did a pretty good job. So I just like, you know, like even the software engineers that are using AI to generate code, like they're basically very important to do kind of like a once over, that everything looks pretty good before even testing it. So like, yeah, I think it did a pretty good job here. So not doing it completely blind. So, all right, so it did. So we have supplier min and max, OAT min and max, which we have to add in, startup delay minutes, update minutes. still don't see an SPO. Alright, so we're gonna have to please make sure we're using okay, so we just want to, let's see, so we have SP Trim, SP Respond. Okay, so I got these, so I'm going to delete them and ignore. Well, I got this, so these are it. So basically it's calling these supplier temp maximum, set point min and max. Or I guess that's fine. Maybe I'll just keep it like that. I think ASHRAE Guideline 36 actually just defines it as SP min, SP max. So SAT min, SAT max. I think it's probably okay. So let's give it a whirl. So copy code from here. So open up our program editor, dump you into there. So then our slots need to be updated. So we need to update SAT min and max. So actually I think like what I might do is just delete these guys, delete you, and let's just make some new fresh ones. So we can even delete our discharge air pressure. So let's do our SP min. We're gonna add some new slots. Status numeric, make it so we can link. Actually, I forgot to change the name. Copy, I think. SP min, status numeric, looks good. Let's go for SP max. Go for outsider min. Click the summary button so we can link outsider max. Summary button. Alright, so then we need to do, this is our, that one, so this will be, alright, so this is our output variable, so we'll make that read only. Here we go. Alright, so like, if I go back to program editor, so we can save it, hit the compile hammer. Alright, we got some errors. Alright, so we got some errors. Screenshot this since we can't copy in Workbench, which is kind of lame. Compile errors, please help. See what it says. Grab some more coffee while the LLM does our work for us. Okay, still thinking. I noticed that ChatGPT 5 is pretty slow. People are kind of complaining about that, and Gemini is pretty slow too. But and it's rewriting for us. See, so it's writing a lot of Java code, just kind of summarizing it as it goes. So I think it looks okay. We'll do our testing at the end. Still kept our little linear interpolate function. Hit the compile button. Ooh, we still got some more errors. I wonder if it's my slot names that are correct. You know what, I think what are my slot names? Not OAT min and max. Let's see, initialize Tmax, get outside air temp. Alright, so let's see, it's where we got some problems. So, cannot find symbol. Get Tmax. So these are slot names. It's looking for Tmax. Calculated. Min SAT. See, we have those. No, ours is SAT min. So this might be kind of annoying. SP min. Let's see, do I have... I think this is the most painful part. So I think it's just some issues with the slot names. Oops. I think the logic is pretty good, but for some reason it's writing some bad slot names, I think. That's what it looks like to me in the compile error. Alright. Go, go, go. Go, Gemini, go. Grab some more coffee. I see the compile errors in the screenshot. It's a very common issue to fix. I can't find it. Methods I've corrected all of the method names in the canvas to match your slots exactly. This should resolve all 12 compile errors. Alright. Take your word for it. Let's try it out. Oh boy. Oh, lovely artificial intelligence. Get Tmax. Tmax calculated. I don't have a Tmax variable. Outside air. Ooh, you know what I don't have is outside air temp. I don't think I ever added that in. So, alright, so we got here. So, hold up. Alright, so I can tell that it is looking for outside air temperature. So this is going to be the slot it's looking for in Workbench. Let's see if this helps cut down some of the compile errors. Okay, so I think I got this outside air temp fixed. Now it's like, what is this Tmax calculated? I don't even remember what temperature max. Where is that? Alright, so let's ask it. What is Tmax? Is that in the NF book that we are supposed to be following to the T? still has that saved in its memory what the normal framework hook was. Tmax. There's Tmax. Internal state for the maximum cooling supplier temperature. So yeah, that is the maximum supplier temperature. So why it needs to have a difference for that? Maybe it's something that normal framework used. Let's see if they have Tmax. Outsider temp max. I almost think that this might be it. Just oh yeah, they do have like a Tmax. Alright, so it is taking this from the normal framework. I think the guys did a good job on this, so like if normal framework has this, you know, let's make it in there too. Yes, that is absolutely okay. Yeah, we did. We followed it too. Following JavaScript to the T as you requested. Is Tmax. Do we need Tmax as a slot? Think. Come on, Gemini. No, you don't need Tmax as a slot. Okay, so let's copy you here. Hit the compile button. Oh boy. Alright, so it's still thinking like we need this Tmax. Alright, so there's stupid artificial intelligence. Tmax. Those are so annoying. Alright, so I'm looking for this Tmax calculated. Tmax calculated. Alright, so says that it removed it. Oh, maybe I just didn't copy and paste it, so it did compile correctly. Okay, so we probably need some. Alright, so we have a compiled working program. Let's move these up a little bit. And then we can start doing some testing. So let's see. We could actually even look in here too. So I want to set these default variables. So this is our trim and respond variables. Time delay, time algorithm update. So they're trimming 0.2 degrees Fahrenheit and responding 0.03, and this is like our maximum value that it will be allowed to respond. So we need to set these. Okay, so back to Workbench. Okay, so we were trim, what was that again? 0.2, 0.03, 1. So this needs to be set as 1.0. 0.2, 0.03. This is a positive 0.2. 0.2. And responding 0.03 negative. So let's set that to minus 0.03. So like basically like the way it responds is it tries to warm up the air on the air handling unit to save energy. Okay, so we have that. See if it's fed into the right slots. Respond max. Okay, so then we just have to set a couple variables for SAT min. Whoops. Duplicate U to SAT max. And then we gotta change this one to OAT min. I'm just following these right here. OAT max. Slide you down a little bit. 10 OAT max. And then we just need a plain out temp. Outside. Let's name this outside air temp. Alright, to connect our wires. OAT max. OAT min. Supplier temp max. Supplier temp min. So here we go. So these can be deleted. And this is also our discharge air temp set point, which I can also already see as a problem that it's outputting 0. So alright, so we'll have to troubleshoot this. So I might stop this video from here and let's go into some testing. Alright, so here we are back again. So time for the fun part, time for some testing. So still in the office environment on my Windows desktop, way before we even would want to install it on a JACE or anything like that. But yeah, let's try and run through some paces. Run this through some paces. So this is the compiled program back in here. This did compile nice, so no issues. We got the green light. And something that I can see right away, we got good variables, except for these. Let's see, so we have our trim respond variable. So let's see, so our supplier temp minimum, actually I think this is an error right here. This actually I think needs to be a minus value. So looking back on the JavaScript code, let's fix that. This needs to be minus. Alright, supplier temp minimum, this one was set to 60 degrees F. Supplier temp max, this was 70 in units F. No, shoot, sorry. This was, I have those backwards. So this was 55 degrees F. And yeah, 70 was the maximum in the United States with a degree F units. 55 is a pretty common design cooling number. And then this is something 70 seems a little high to float the air handling unit supply air temp up that much, but I think it'll work fine for what we need it for. So then this is our linear interpolation. So at 60 degrees and then 70 degrees. So this is our lovely humidity checker that if the outside air temperature is above 70 degrees, we're gonna lock it in at 55. And these are tunable too. So just stating that if it's in the United States, if it's above 70, even closer to 80, more than likely, especially where I'm living, it's gonna be really humid. So we need that 55 number for dehumidification purposes to do that sensible and latent cooling load. All right, so let's look at our algorithm. So we have a leaving temp set point of 1. So that does not look good. Let's try toggling our fan off and on. All right, so that might have done something. So what the logic is supposed to do when the fan is off, that we resort to basically our SAT max number. If you remember in the JavaScript code, they were calling it your max cooling. So it's basically, it's a default number that when we're in startup mode, as with the duct static pressure reset algorithm, that we have like a startup value before we start trimming and responding after our startup delay expires. So it did that. It's it might have been screwed up because these variables were not set right. So that's why we test software before we put it in the field. So put you back to true. So the fan started. So our status trace. These are string writables. You could even put these on Tritium graphics. I like it, so I can see like what the algorithm is doing. So basically it jumped immediately. So our fan started, we simulated the fan starting, and then I can tell that, see, it's counting down right here every 10 seconds until our startup delay timer expires, which is that's internal in the Java code. Like we have that as part of our algorithm. So like what I could do for just simulation purposes is like we could put this down to 0.1, put you down to 0.1. Okay, so we're gonna simulate it really fast. All right, so we jumped already, we're out of the mode, our startup mode. And so we should be simulating really fast. So our ignore requests is 0. Okay, so this is our requests variable input. If you remember, this comes from these guys. So this is maybe I can show you this. So my user home. So this was something I created previously. This is cooling request. So just paste you in just to show you what it looks like. So like this is just the requesting logic for a VAV box for cooling requests. So basically we're just defined by guideline 36 that if we're over set point, and they also factor in this zone demand point, that we calculate requests value of 0, 1, 2, or 3. So we could have 10 VAV boxes, there would be 10 of these things, and we'd be summarizing all of these requests, which would all be linked to here. So the air handling unit program will know the maximum amount of requests for the system, which is fed in here. So right now, because there's no requests on the system, we're at our maximum cooling, which is 70. which is this variable here. So that's like the maximum value that we'd float the air handling unit up. So let's just say, let's set you to 9. I don't know. Let's say there's 3 VAV boxes, both with 3 requests, the maximum value that a VAV box can do. So then we should start trimming the air handling unit down. So it's responding. Looks like we're responding good. So because we're simulating this really fast, but the thing that we need to take account for that ASHRAE Guideline 36 states is this SP maximum it can respond. This is like a time delta. So in the event that there would be a huge number of requests like we just simulated, it's only going to let it respond 1 degree. It'd be really interesting just to see if we can see where that lives in here. So this should be a time delta calculation. I just want to see how it's handled in Java. So yeah, let's see if we can, let's ask AI where it handling this. Where in the Java is the algorithm handling the, which is a very important part of G36. Other than that, just verifying that critical part. Okay, so it is factoring it in. Just I want to make sure that so it never be seen more aggressive. Okay, so let's see this. Sure that we can do some, whoops, try and do some due diligence here. This very limited. Okay, yeah, so it is actually keeping it, it's right here. It even says, look at here, that the normal framework hook calculated new Tmax based on, okay, so it's factoring in this, here's a respond maximum amount. So it's only going to let it respond by 1 whole degree, 1 negative whole degree, depending, you know, even if every VAV box in the system generated 3 requests each, the algorithm without this could make the whole leaving air temperature set point, you know, respond a huge amount, but this kind of prevents that from happening, so we have that built in. So okay, so back to some more due diligence. All right, so with our fast simulation here, we trimmed it all the way down to 55 degrees with our 9 requests. So if I set this, let's set this to 8. Because we have an ignore request of 1, so now we should be responding back up. So we should be. Wow, that did not respond the way I thought it did. So I think we have. I think I just saw a glitch. saw something that looked really funny, that we had variables, so something, wait, hold up. So we need to set this to a value of 1. So if we have a request of 1 and we're ignoring 1, this should cancel out and there should be really 0 requests on the algorithm, and we should be warming the temperature back up. So basically the guideline 36, when there's a call for cooling from the VAV system, we meet that demand by cooling the VAV system down. And if there's no call for cooling, we warm the air handling unit set point back up, which would, if it's in a cooling application, take the load off the chiller and save electrical energy. All right, so it looks like we are trying to do that, where the algorithm is warming itself back up, which looks pretty good. I can see us, algorithm is counting back up. All right, so let's simulate some more requests. And we should go back down. Responding. See, we just responded, so it looks like we're starting to calculate down. I think it's looking pretty good. Just want to see it actually count down. Unless it's actually holding out from like the time delta calculation, which actually did. Okay, so like next thing I want to try is maybe cranking up our outside air temperature. Let's simulate it to hot, humid. If it's 88 degrees Fahrenheit in the middle of Midwest United States or Canada, it's going to be really humid. So this worked. This actually made our algorithm go right to 55. Kind of clamped that in. So basically, when the outside air temperature is above 70, we're going to lock it in right at 55, which it did. I think I'm actually pretty happy with this. So even if I set that to 0 requests in the system, even with us still in hot, humid, we still should be locked in at 55. So it's I think it's looking pretty good. I also think that some more research should be going into how to tune ignore requests. I know that if it's really small VAV systems, that having the ignore request variable set at 0 can prevent comfort complaints, and people should kind of pay close attention if there's like a computer room or a copy machine room, that more than likely you could be excluding that VAV from these calculations. But I don't know if there's any general rules of thumb, but you could, if nothing exists, I'm going off of setting this to 1 per 10 VAV boxes. So if there's less than 10 VAV boxes on a multivariable air handling unit system, I'm setting this to 0. If it's 10 to 20, I might set it to 1. 20 to 30, maybe to 2. If it's 30 VAV boxes, a big system, we could set this as 3. But then it's all totally dependent on what kind of building it is and what it's serving. So this is very important that someone is going back and tuning this and seeing if comfort complaints, all that good stuff. So, all right, so I think I might actually stop at this video. I feel pretty happy. Next thing I'll be doing is putting this on the JACE after checking my resources and linking up a lot of VAV boxes to this request input, as well as my outside air temperature. So yeah, I feel pretty good. This is just a quick example how to vibe code and do some testing in the office before the field. All right, I also forgot to say that you can also in platform use the application director to see if there's any issues like in your program. So like here I'm using these status strings because I kind of like it, and plus like when I'm on the live system, I might not have access to platform if it's someone else's JACE. So I can see these status strings. So I mostly use these for debugging, but you can also put print lines in here too, where they will show up in the application director in here. So like, I think this was us before when we were debugging, but you can see if you have access to platform director, it can help. So I'm just gonna clear the output and just make sure that my programs are still looking good. So, and they are. So I think I feel pretty good about, you know, putting this on a live system. And like another thing, like, you know, just to keep on studying, you know, just one final note in here, like I'm still do a little bit of my try and do like a lunch break every day as like study like a little bit. I think Coursera is really good, so I'm actively doing this Codio course for Java data structures and algorithms. So it's this is really good, and it's getting like really hard too, but so it helps me kind of think. I don't have that computer science degree, but this is helping me get those fundamental to be able to think like a computer scientist, just that fundamental skill set, where I think like if you're generating data from a large language model, the more that you have of this computer science theory, you know, like the better, faster, stronger that you'll be at vibe coding this. So yeah, it's kind of taking this and your HVAC control background, and you know, you can make some pretty powerful stuff. And yeah, stay tuned. So thank you for making it this far, if you made it this far, and we'll catch you on the next go around.